Hey everyone, welcome back to the Chem 115 video help series. During this section of material, we are talking about a couple of different topics, but we are going to start off with our discussion of the periodic table and how to read it. This video will prepare us to be able to use the periodic table to make predictions about bonding and prepare us to learn about the process of naming compounds. If this doesn't apply to you and you feel very comfortable reading the periodic table and basic atomic structure, feel free to skip on this video and join us next time. So let's look at a periodic table for reference. So if we look at the top of this periodic table, which can be found in y'all's textbook or online, there is this blue numbering across the columns and a word that says group. Now the thing to note here is that these columns are labeled as groups or groupings within the periodic table because all of the elements within, say, group 1, which is the one that I've circled, have a collection of very similar properties, such as how they conduct heat and electricity, reactivity, other chemical properties that you'll talk about later in this course, and so forth. That's all you really need to know about groupings right now. Now, there is another relationship which is demonstrated by this red numbering across the rows, in the word period that is also in red. Now, we won't discuss here why we use the word period at this very moment, but basically, if you look really closely, there's a relationship involving the numbers at the top of these boxes, which I'll circle. You can see with lithium, there's a 3, beryllium, there's a 4, so on and so forth as we travel this way, where this number is increasing as they move from left to right across the period or the row, increasing until they hit the last element on the right, which in the second period is neon. So increasing until we get to that last element on the right, and then moving down to the next period, the third period in this example, which starts with sodium, and continuing on in that same trend. So you may be asking, well, why is this number at the top increasing? Why have we grouped these elements in periods, etc.? And that's a good question. To answer it, I want to talk about orbitals using a very simple atomic model. So this is a simple atomic model for lithium. It represents electrons which have negative charge of -1 attached to them as orbiting the nucleus, which is the center bit right here. The center contains both neutrons, which are neutral particles, they have no charge attached to them, and protons, which have a positive charge attached to them. The electrons orbit the nucleus in shells. You can see I've drawn a shell here, which is a circle with 2 electrons, and a shell right here. The first shell in every atom contains just 2 electrons, which is what I've drawn right here, 1, 2. Whereas the rest of the shells, as you progress up, contain 8 electrons, or up to 8 electrons. In a neutral molecule, the number of electrons is the same for the number of protons. Here I've drawn a neutral lithium atom, which is why we have the number of protons represented in red, totaling the number of electrons, which are here in blue. So even though my lithium atom could potentially contain more electrons, up to 7 more in the second shell I've drawn, because I've drawn a neutral lithium atom, I have only drawn 3 electrons in, 2 in that first shell, as the rule states, and 1 more, the last of the 3, in the second shell. Most importantly, one of the things that I want you guys to take away is that the number of protons is what defines the identity of the atom. It does not change. So for an example, the lithium atom always contains 3 protons. The fact that it has 3 protons is what defines it as a lithium atom. You can tell how many protons an atom has by this number at the top, right? So if we look to lithium, it says 3 right there. Basically, the differing periods are representing the number of shells of electrons. When the first shell fills, as we can see here in helium, as it takes only 2 electrons to fill the first shell, the next electron, would be the third electron, which is prevalent for lithium, must move into the second shell. This trend continues, with the next 7 electrons that are added in going into the second shell, which would be these electrons remaining in the second period, until you get to neon. Once you add in the 8th electron to like a lithium atom, it has to go and create a new shell. This is where we get the octet rule from. From periods 2 and on, 8 electrons can inhabit one of these shells before we have to move to the next period. The octet rule helps us to understand what is meant by these numbers across the top of the periodic element box and why elements are also organized by period. The elements in the same period have outer shell electrons, known as valence shell electrons, that exist in the same shell as other elements in that period. Cool. So as you can see, it is very helpful to be able to construct these simple atomic models because it can help us understand and show lots of different things that we're going to see in this class, including representing the periodic table, bonding, all of that good stuff. So I'll make sure to include some practice with this so that you can be able to draw these too. Another thing to note that you can probably see from your periodic table is that there are different colors on that table. These colors represent very general classes that elements have been grouped into based off of their similar chemical and physical properties. Now, while their names aren't super important to know, it is probably a good thing just to review just in case they're on your exam. It's also helpful generally to know that these groups are different from each other. Now, there are other really great ways to classify and name periodic table elements. Your book provides a really good example of another one, which is this. However, I wouldn't worry too much for the scope of this class about the actual names of the groups. What helped me to know about when I took this class was that these are the transition metals, these are the noble gases, and knowing where my metals versus my nonmetals were. Those were all that I really needed to know at this point in the class, so that's what I'm recommending for you. Finally, it is important that you know how to read and interpret the periodic table boxes. Here's the one for hydrogen as an example. Now again, this is atomic number. It represents the amount of protons, which tells us the identity of the atom. Every hydrogen atom always has 1 proton. That is what makes it a hydrogen atom. The symbol is really quickly just a way to say, now this is hydrogen, and then there's the name, of course. Now, the only thing that we haven't gone over from this periodic table box is atomic mass. The definition that we will use for right now is that the atomic mass is the quantity of matter in an atom of this element. The thing that I want you to take away is that from the periodic tile alone, we can elucidate parts of atomic structure related to the simple atomic model that we used earlier. Using hydrogen as an example, I'm going to show you how to do this. First, recall that the atomic number is the number of protons in an atom and is the number of electrons in a neutral atom, so we can write this down here. Now, the only variable particle here is the number of neutrons in the nucleus. I'll just say in this example that there is 1 neutron for now, but there can be more or less, dependent on the atomic mass for the particular atom, which I will talk about in a later video. Now, we think about where these things exist. We talked about how the protons and neutrons exist in the center, the nucleus of the atom. So we draw these here like so. Sweet. And since hydrogen just has 1 electron in this example, since we're drawing a neutral hydrogen atom, we can see this electron is just hanging out. Sweet. So just as a review for this video, we now know how to read the periodic table to tell us about properties of atoms. We know the basis of atomic structure, And we know how to read a periodic table tile to tell us about an atom's basic structure. Great job, guys. There are going to be some more practice questions to really solidify this knowledge in the same place as last time. Have a good one.